Okay. So good evening, everyone. I am Alberto Ciampaglia from Politecnico di Torino, and today I'm presenting you a data-driven method for predicting the fatigue response of the additive manufacturing metals from the process parameters. I've been developing this method together with Professor Tridello and Professor Paolino from Politecnico di Torino and Professor Alberto for Sapienza University. So, as you know, the fatigue response of metals can be modeled by well-known formulation, while the fatigue strength at a finite life can be computed starting from the fatigue limit of the material. So, the fatigue limit itself, according to the Murakami formulation, can be described by this formula, where we can distinguish two main factors. So, the first one is the vigorous hardness, that according to Murakami is related to the microstructure of the material that we are characterizing. And second one is the area of the defects. So when we deal with the additive manufactured metals, both the microstructure and the defects are dependent on the process parameter itself. So from there, the idea to model the fatigue response of the additive manufactured metals starting from the process parameter itself. To do that, we use the machine learning approach. So the machine learning approach, you need a database. So we have collected a bunch of experimental data on process parameter and the fatigue response of aluminum alloy printed with additive manufacturing. And we used a neural network to find the relationship between the process parameter and the fatigue response. So the neural network is one of the most common machine learning architecture, where the input is propagated toward the output through some stacked layers. Within every layers, we have some neurons, and within the neurons, we perform a very basic operation where the inputs are weighted, summed up, and passed through an activation function A. So the parameter of our neural network are the W and B, and these are trained with a training data set. So a bunch of data where we know, in our case, the process parameter and the fatigue response. So the advantage of this method is that neural networks are universal approximators, so you can approximate any function if you have sufficient amount of data. So this can be a restriction in terms of experimental mechanics, and also the prediction could be physically inconsistent because we do not predefine the model before the modeling itself. So there is a different approach that can be used to overcome this limitation of neural networks. That is the physics-informed neural network. So if we have some knowledge that puts in relation the input and the output of our model, we can use this knowledge and infuse to the neural network and build a physics-informed neural network to enhance the predictive capability of this tool. The main advantages when we use this approach is that we can have good prediction with a smaller data set, because we basically confine the domain of the solution, and we can have some physically guided prediction that is strictly fundamental in science, of course. So the way we did that, so we propose a modified architecture of our neural network to use the physics knowledge that we have seen before. So starting from the processing parameter of the selective laser masking process, we divide it in two different branches. So a first branch predicts a microstructure latent variable, and the second one predicts a defect latent variable. Then these two latent variables predicted by two different neural networks are fitting a second block where we mimic the Murakami equation. So we compute a ratio between this microstructure latent variable and the defect latent variables and combine it with the number of cycles to predict the fatigue strength itself and get the fatigue response starting from the process parameter. We trained both the standard neural network and physics-informed neural network using a loss function as a mean square error loss function, and we achieved a 20% better performance and better accuracy of the physics-informed model. That is shown here, where we compare the prediction of the neural network on the x-axis with the experimental observation. Of course, the fatigue response has some scatter that these deterministic models cannot capture itself. So there is an uncertainty band of 50 megapascal that has been that is shown in the picture. But overall, we can say that this method can predict the fatigue response of this metal under different printing parameter, even with the resulting curves are very different between them. And another advantage of this architecture is that the predictive capability is also better behind the observed domain during the training, because we're infusing some physics that is preserved even when we are predicting outside our dataset. So for example, if we take a look at some dataset where we have some data until 10 to the 6th number of cycles, we can see that using our method, we will have a reliable prediction or a physics compliant prediction even in very high cycle regime, because there was some data from the very high cycle regime and neural network could learn the relationship between the printing parameter and the response at that regime. And this can also be used. We have been validated also this network against some dataset that was not present in the training dataset, of course, where one parameter for the printing process was unknown. And by varying the unknown parameter, that is the beam diameter in this case, we get a band of the prediction. And we can see that the experimental data falls within the bands with an acceptable accuracy. And this tool can also be used to investigate the influence of one single parameter on the fatigue response. And again, we have tested our network again, an experimental dataset where a specific design of experiment was designed to study the effect of the edge distance on the fatigue response. And we compare on the left the black box approach where we have a standard neural network, with the right our proposed neural network with a physics informed approach. And we can see that neural network is able to capture this trend accordingly to the experimental data. So this means that even if we don't have a well-designed experiment properly thought to explore the effect of this parameter on the fatigue response, learning from a big data set with sparse data, the machine learning approach is able to approximate and predict the interaction of different parameters anyway. So arriving to the conclusion, what we have achieved with this project is the development of a physics-based data-driven model that can predict the fatigue response starting from the printing parameter. So we believe that is a useful tool in the end of the designer that need to set the printing parameter beforehand before printing their part, with an overall good accuracy that can learn the interaction between the different parameters and how they affect the microstructure and the defects, and as consequence, the fatigue response. And fatigue curves resulting from our method result physics compliant with the physical trend that we know for the fatigue. So due to the time constraint, I didn't go through the details of the method, but an article has been published about this methodology that you can find scanning the QR code on the left. On the right, there is QR code for a special issue on machine learning for fatigue design that our research group is managing on MDPI. So thank you for your attention.